Hi, today we'll see new topic is quantum mechanics. In quantum mechanics, first we'll start with the de Broglie's hypothesis. The de Broglie hypothesis is that according to de Broglie's hypothesis, a moving particle always has a wave associated with it, and the motion of that particle is guided by that associate the wave. Before that, we have seen the dual nature of particle, dual nature of light, in which light sometimes shows nature of particle and sometimes nature of wave. So this de Broglie gives the relation between that both when particle wave act as particle and light act as waves. The wave associated with particle are known as matter waves or de Broglie wave, and these relation is given by the equation lambda is equal to h upon p, where lambda is the wavelength of the de Broglie wave, h is the Planck constant, and p is the momentum. So in the single equation, we can observe here is the wave nature and here is particle nature. Cause wave having wavelength, that's wave having wavelength, and this any particle having the momentum. Momentum is mass into velocity. Next, the expression for the wavelength of matter wave or de Broglie wave can be obtained by the analogy of the behavior of radiation with matter. So we can obtain the relation, this relation lambda is equal to h upon p by some analogies, like by the Planck equation, which gives the energy of photon. That is very famous equation that you already know, which is E is equal to h nu. Let equation number 1. Again, we know another equation, the Einstein equation. So by Einstein's mass energy relation, which is E is equal to mc square, will give you the equation number 2. From equation 1 and 2, if you observe, this is equation 1 and 2, both are the equations of energy, so we can equate it. That time we can write from equation 1 and 2, h nu is equal to mc square, where h Planck constant, nu is the frequency, m is mass, and c is the speed. Let this equation number 3. Now, if p is the momentum of photon, p is the momentum of photon, that is p is mass into velocity. Here, just velocity we consider as c. So p is equal to mc. So in equation 3, which we have already written, h nu is equal to mc square. So that mc square we can split into mc into c, and that one mc we can write as a p. So mc square we can write p into c. So equation number 3 we can write h nu is equal to pc. Here again, instead of c we can write substitute as c is equal to nu lambda. The speed is equal to frequency into wavelength. Now in this equation, h nu is equal to p nu lambda. In both sides, nu is common. We can cancel it. So remains will be h is equal to p lambda. Now just rearrange this. We can write this lambda is equal to h upon p, which is the equation of de Broglie's wave. Now we can obtain this de Broglie wavelength in terms of kinetic energy. For that purpose, we already know what is de Broglie wavelength, which is lambda is equal to h upon p. Now Consider a particle of mass m moving with velocity v. Its momentum will be p is equal to mv, and the de Broglie's wavelength of matter wave associated with it is given by lambda is equal to h upon p. This p we can substitute as mass into velocity. So lambda we can also write h upon mv. Let equation number 1. The kinetic energy of particle is given by E is equal to half mv square. Here m is the mass of the particle and v is the velocity of particle. The general equation of kinetic energy. Now we have to substitute these. We have to substitute these in this equation. So here h and p, in terms of h and p, h is constant. So we have to change this is equal to half mv square in terms of p, and we know p is m into v. If you observe these, here m into v square and momentum is m into v. So we can rearrange this by taking p adjacent p square here. To get p square, you have to multiply this side with m and also will divide by m. So this equation we can write as E is equal to these equation multiply and divide by m. So here m square, v square, and again divided to m. So equation is E is equal to 1 upon 2m into m square v square. Now here instead of m square v square we can substitute p square. So equation becomes E is equal to p square upon 2m. Next, so we just rearrange this in terms of p square. So p square is equal to 2me. Now we want value of p. So we take square root of both sides. So it will be p is equal to under root 2me. That equation number 2. Now by putting the value of p in the equation of matter wave, which is lambda is equal to h upon p. So de Broglie's wave becomes h upon under root 2me. This is, or we can say this above equation gives the de Broglie's wavelength of particle of mass m and kinetic energy E. This equation is true for any particle irrespective of its charge or mass. Next, the de Broglie wavelength in terms of accelerating potential. If a charged particle such as electron or photon of rest mass m0 is accelerated by a potential difference v holds, the kinetic energy gained by it is given by E is equal to small e into v. This is kinetic energy is equal to small e into v, where the small e is the charge and v is the potential. Now this kinetic energy we can now write as again half mv square. Here only instead of normal case there is m, here we have written m0 because here we are considering rest mass. So it becomes half mv half m0 v square, which is equal to e into v. Now again we have to rearrange these equation in terms of p. So to get p square, again we multiply this side with m and divide with m. Here instead of m there is m naught. Now we'll take these two m naught to other side, so it gives m naught square v square is equal to 2 m naught ev, which is p square. Now to get the value of p, we have to again take its square root. So it gives uh, p is equal to m naught v, which is equal to under root 2 m naught ev. So this p we can substitute in de Broglie's wave. Thus, the de Broglie wavelength associated charge is given by lambda is equal to h upon p equal to h upon mv. So here we can put the value of m naught v or p, which is under root 2m ev. So from equation 2 and 3 we can write as lambda is equal to h upon root 2m naught ev. This is equation number 4, and this equation number 4 gives the de Broglie wavelength of an electron when it is accelerated by potential difference v. Now as we have written, lambda is equal to h upon under root 2 m naught ev. Here h is the Planck constant having value 6.63 into 10 to the minus 34 joule second, and small e is a charge on the particle. If you consider the electron, then or elementary particles, then its charge is 1.6 into 10 to the minus 19 coulomb, and this capital V is the applied potential. Now for electron, we know the rest mass, value of rest mass is m naught is equal to 9.1 into 10 to the minus 31 kilo, and we already know the value of E for electron, which is 1.6 into 10 to the minus 9. So instead of m naught, if we put the value of 9.1 into 10 to the minus 31, and value of H is 6.63 into 10 to the minus 34, we can get the value of wavelength as lambda is equal to 12.27 upon under root V, this value in Armstrong. So we are getting de Broglie's wave for rest mass value. For your sake of understanding, you can put this value and check by calculation where you will get the same value. Now for proton, we can find the de Broglie's wave by using rest mass, which having value is 1.67 minus 27 kilo. So if you put this value in this equation, then we'll get lambda is equal to 0.286 upon under root V Armstrong. Okay,